string pheno. Maybe I should also remind you all that even though this is the last day of the String Pheno conference, there will be an ongoing series of String Pheno talks that John and Cody are organizing starting on Tuesday, and I'll paste that link in the chat window again if anyone didn't get that before. Okay, so should we get started with the first talk? Yinan, are you ready?
Yep, gonna share my screen.
Okay.
And perhaps now, in the interest of bandwidth, as talks are beginning, if everyone could mute themselves and turn off their video, that would be great. Thanks.
Okay. Yeah, so for the first talk, we have Yinan Wang from Oxford, and he's going to tell us about the boundaries of the 4D F-theory landscape. Yinan?
Okay, I can start. So first, I'm gonna thank the organizers for inviting me to this great online conference. So today, my topic is about the boundaries of 4D F-theory landscape. In particular, I'm gonna mention the following a few papers. I'm gonna mainly focus on my recent work about the 4D F-theory on the elliptic labial fourfold with maximal H11. And I'm also going to shortly mention the previous two papers with Watty Taylor on the scanning of 4D F-theory landscape, and also the particular F-theory geometry with largest number of flux vector. Okay. So first, I'm going to give a brief overview about the paradigm of the landscape versus one-plan question. So let's consider the space of low energy effective series coupled to quantum gravity. And then, so the smallest set you can see here is a known string landscape that has a well-known construction in the current string theory framework. And then at outside, we have a bunch of apparently inconsistent series. And between those two sets, I define the swampland series to be the low energy series that are apparently consistent, but they haven't got any known string construction yet. Okay, that is a swampland. So now in this set picture, we have two very important boundaries. The first one is the boundary of string landscape, the currently known string landscape. And we also have this outer boundary, which is a swampland bound. And this is also a very important topic of this conference, of course. Then in order to progress in this picture, we can do one of the following two things. So we can either try to enlarge the boundary for the currently known string landscape, or we can try to refine the swampland bound. So finally, if you are going to assume that the string universality conjecture is true, such that any UV complete consistent quantum gravity series can be constructed in a string theory setup, then we can finally completely drain the swampland, and we will end up with a picture below, where you only have a well-defined string landscape and an inconsistency series out of it. And now we will have a very clear, well-defined boundary for quantum gravity. So that's our hope. So in this talk, I'm going to focus on the discussion of the inner boundary, that is the boundary of string landscape. So in particular, the question I'm going to ask about this boundary is as follows. First, we have to fix a particular space-time dimension and the number of supersymmetry. And the question is, in the low energy effective theory, what is the upper bound of a certain type of fields coupled to Einstein gravity in the same dimension? For example, this type of fields can include, for example, the vector multiplet, also axion scalars, or tensor multiplet in certain dimensions, like in 6 dimensions, we have these tensor multiplets. So below, I will give you a very quick answer, which are the take-home message of this talk. So in the currently known string landscape, for the 4D n equal 1 supergravity, the maximal rank of gauge group and the maximum number of axion fields coupled to a supergravity are at the order of 10 to the 5th. For the higher dimensional series like 61,0 or 5D n equal 1, then the maximal rank of gauge group and the maximum number of tensor multiplets are all at the order of 100. Okay. So now I'm going to go into the first part of this talk, which is about 40n equal 1 supergravity, where the masses supermultiplates are supergravity multiplates, vector multiplates, and chiral multiplates. In string theory, there are many different ways to construct 40n equal 1 series. That include, for example, F0 on elliptic Clavier fourfold, heterotic string on Clavier threefold, or M0 on G2 manifold. Of course, there also exist many Wiki couple description, like intersecting brane models with type 2A superstring in presence of D6 branes. So in this talk, I'm going to mainly focus on the first class, which is F0 on elliptic Clavier fourfold. The reason is just that it will turns out that this particular landscape will provide the known upper bounds to all the previous questions about the maximum number of fields coupled to gravity. Okay. So in this sense, you may interpret it that F0 is probably the largest one among all the string landscapes. Although we know, of course, F0 is not everything, and there exists, for example, hydraulic string complexification that cannot be due to F0. So now I'm going to give a brief overview about the setup for the F0. So the particular geometric object we are going to consider in this talk is a possibly singular elliptic Clavier fourfold X4 fibered over a smooth space threefold B3 in terms of the following Weierstrass model. The functions f and g are holomorphic sections of particular line bundles on the smooth space threefold B3. The particular important quantity is a discriminant function delta. So when this function vanishes, the elliptic fiber over the space loci is singular. So there are multiple different types of this discriminant locus. Depending on the particular codimension of this loci, they could encode various different kinds of 4D physical fields. So for codimension 1, 2, or 3, there could be 4D non-abelian gauge group or Wiki couple matter fields, or you cover coupling terms localized on this discriminant locus. Okay, so that's pretty well known. But there's also an important point I want to say here. So for this physical field, I always require that the order of vanishing of these functions, Fg and delta, is lower than a certain value, that is 6, 4, 6, and 12 for Fg and delta. This is also known as flat vibration condition in the elliptic vibration. So you may wonder what happens if this bound is violated, and I will explain this point in more detail in the next slides. Okay. So finally, I'm going to point out that later when we talk about topological quantities, like Hausch numbers of the Clavier fourfold, we are always actually referring to the equivalent resolution of X4, which is denoted by X4 hat. So after the equivalent resolution of this singular Weierstrass model, basically, you end up with this X4 hat with at most terminal singularity. Okay. So now let's go into more detail on the so-called non-minimal loci where the order of vanishing of this function is higher than this bound. So this is actually pretty interesting since there are multiple different types of this non-minimal loci. So I list all those cases in this table according to the order of vanishing of these functions, like whether it's 4, 6, 12 or 8, 12, 24 or it's even larger numbers. And the codimension of this non-minimal loci, they could be either codimension 1 over a divisor, or codimension 2 over a complex curve, or codimension 3 that's over a point. Okay. So for example, if the order of vanishing on codimension 1 that's a divisor is bigger or equal than 4, 6, and 12, this is called codimension 1 locus, or if the order of vanishing is bigger than 8, 12 on codimension 2 locus, or 12, 18 on codimension 3 loci, then what happens is that this geometry of Clavier fourfold is pretty bad in the sense that the singularity of X4 is worse than canonical. So in the purpose of this talk, all these cases are strictly forbidden, and also because physically, these geometries do not support any consistent supersymmetric vector. So, but then you may, if the order of vanishing is not too high, so the singularity is not that bad. For example, if the order of vanishing of Fn delta on the coordinate 2 loci is bigger or equal than 4, 6, 12, but not too high, then there will be some very interesting physical sectors localized on this loci. So in this case, an interesting thing is that there are two different choices we can do. So one can either choose to blow up this curve on the base threefold so that the B3 becomes a new base B3 prime. Then what happens is that over this new B3 prime, the EDP vibration X4 prime, you will not have any of this non-mu loci anymore. Another very interesting phenomenon is that if you consider the Krypton resolution of this new Calabi-Yau fourfold, it will exactly have the same Harsh number as the old one. Okay. And alternatively, one can also choose to directly study the non-flat vibration over the old base B3. And in this case, there will be some strongly coupled matter fields localized on this curve. For example, it can be a dimensional reduction of a 6-dimensional 1,0 SCFT on this curve, complex curve. Okay. Now, similarly, we can also consider a dimension 3 non-mu loci. You can also either try to blow up this point on the base or directly study the non-flat vibration over the old base. In the later case, there will also be a strongly coupled sector localized at this point. And this was studied by this 4D conformal matter paper by Fabio Abruzzi, Jonathan Heckman, Dave Morrison, and Luigi Tizzano. Okay. So in this talk, I'm mostly going to use a notion of the so-called good vibration, which is defined to be the elliptic vibration without any of the non-mu loci I just mentioned. But the physical importance of this definition is that one may expect a weakly coupled description of low energy theory actually exists. Nonetheless, even in the definition of good vibration, we also allow a number of non-mu loci, such as the coordination 3, 4, 6, which encodes some interesting higher order coupled coupling. And we also generally allow the appearance of terminal singularities. Okay. So mathematically, the importance of a good vibration is that the following Tate-Shields-Lavoisier formula can be applied to compute the Harsh number H11 of the Calabi-Yau fourfold. The formula is just that H11 of X4 hat equals to the H11 of the base threefold plus the total rank of geometric gauge group plus 1. And this formula will be also mentioned in the later part of this talk. So now, if we want to perform a classification program of the compact 4D X-ray landscape, then there are 3 different steps we need to do. So first, we need to classify the different topologies of all the compact base threefold B3. And then over each B3, we want to classify different vibrations that lead to a bidirectional Euclidean equivalent X4 hat. And after we fix the geometry, we have to include a very important ingredient in the amateur reduced picture, which is the G4 flux choices, which is crucial for having a chiral spectrum and also moderate sterilization, etc. It's also notable to mention that the number of such G4 flux choices is always bounded by this type cancellation condition. So on the left-hand side, we have the number of D3 branes in 4D F3, and on the right-hand side, we have a quantity evaluated on the resolved Calabi-Yau fourfold. Okay, so this is a brief overview for the F theory. So now, if you want to classify all the geometries, then you may wonder what is known mathematically about the Calabi-Yau fourfolds. In fact, even more than 20 years ago, many people have constructed a large number of collabial fourfolds as hypersurfaces in ambient 5-dimensional toric space. So here in this following plot, this is a so-called Kruskalk database of collabial fourfold. So each point here denotes a collabial fourfold with a different hash number, and the horizontal and the vertical axis are the H11 and H31. So now there are a few remarkable things you can read out from this diagram. The first thing is that, as you can see, this picture has a reflection symmetry along its 45-degree axis. This is just because of mirror symmetry, which exchange the hash numbers H11 with H31. This is expected. Another very important phenomenon is a so-called shield structure like this. So there's a shield with 3 almost right triangles, almost right angles. So basically, any point above this shield is somehow forbidden in this landscape of collabial fourfolds. The third remark is that the largest number of hash number is at the order of 300,000, and this will also be mentioned later. Okay, so this is for the general collabial fourfolds. So what about the elliptic collabial fourfold that support the 40F theory? So a few years ago, two mathematicians, Disturbo and Spaldi, has proven that the total number of elliptic collabial fourfold up to isomorphism in quantum machine 1 is finite. Now this is also mentioned in Cody's talk. So a very important implication is that the number of all the possible hash number combinations and the upper bounds on these hash numbers is also finite. So this basically validates our previous question and our approaches to try to classify those geometries. And for the topology of the base threefold, this is following Folk's law in the minimal model program of algebraic geometry. So this B3 has to be one of the following or a blow up of either a funnel threefold or a B2 complex surface B2 over P1 or a P1 over B2. So this is basically what is known mathematically on this subject, is kind of limited. As a physicist, in the recent few years, there have been many different systematic approaches that try to classify the set of base threefold and also the collabial fourfold over them. So the first work in this field is a paper by Jim Harrison and Wattie Taylor in 2015, where they restricted the form of base threefold to be a P1 fiber over B2. And after that, me and Wattie has done a random flop approach, where we just start from a simple base like P3, and we do some random flop, and then we can study the properties of the bases we scanned using some statistical methods. Okay. And of course, after that, there is very interesting work by Jim, Cody, and Ben Song, which systematically blow up a weak final toric threefold. And they also prove this lower bound 10 to the 755 on the total number of base threefold, which allows the appearance of non-minimal loci actually. After that, me and Wattie has also done a different random blow-up approach, which further increases this lower bound to an even bigger number. But now it's important to remark that actually for all the geometries appeared in those scans, they lies in a very restricted corner of the whole landscape of collabial fourfold. So if you plot the hash number of collabial fourfold, then you can see that it's all lies very close to the origin, so the numbers are very small. And for the vast majority of this landscape, so for all this data point over here, they have not been studied yet. Okay. So now I'm going to further say a few more words on this last approach, the random blow-up approach. So what we do here is pretty simple. So we just start with a base like P3, we do a number of random toric blow-up, and we finally hit an endpoint. It's an endpoint because any further blow up will lead to a very bad base, like only supports convention 146 or something. But in this approach, there's a very curious phenomenon we have found. So somehow, if you just do this, 15% of all the random blow-up sequences will hit an endpoint base with a certain hash number H11, which is like 2303. So here I plotted the distribution of the endpoint bases as a function of H11. As you can see, the distribution is very discrete. It's not continuous. So then you have to conclude that there exists some very mysterious hidden structure in the set of these endpoint bases. And I will answer this question in the later part of this talk and trying to solve this puzzle. Okay. So now let's go back to the main theme of this talk, which is the boundary for the F3 landscape. So in this picture, if you want to try to find some for the F3 model with largest number of physical fields, the natural point of interest are the ones with the largest hash number, either H31 or H11 located here. So in particular, for the Clavier forfold with largest H31, this was studied by a paper by Wang and me in 2015. So in this particular model, it has the largest number of complex structure moduli and the largest number of G4 flux choices. On the other hand, for the elite Clavier forfold with the largest H11, at this point, so geometrically, this is exactly a mirror of that guy, as you can see from the reflection. So this particular for the F3 model will contain the largest gauge rank and the number of axions in the known for the N=1 string landscape. Okay. So first, I'm going to talk about basic results on the EDP Clavier forfold with the largest H31. So in this paper, we have explicitly constructed the base threefold as a B2 fibration over P1, where the B2 is a base surface for a very interesting self-mirror EDP Clavier threefold. So the 40 geometric gauge group in this case is a product group of a bunch of E8, F4, G2, and SU2. So this is, in fact, this is a very typical form of non-hito gauge group in the vast majority for the F3 landscape. On this particular geometry, we have also estimated the total number of G4 flux choices via a very simple method. So we approximate this problem by a counting problem of the number of lattice points in a very high dimensional ball with a certain radius. So we have found out that the total number of flux choices is at the order of 10 to the 10 to the 5, either with or without self-duality condition. Now this number is the biggest among all the possible geometries simply because both the dimensions and the radius are the largest as possible. Okay. And here I'm going to make a remark that this method is very crude and there could be some systematic overcounting problem due to the non-trivial metric of the space of fluxes. So this point was studied by a recent paper by Miranda Chen, Greg Moore, and Natalie Paquet, although they only look at the Clavier threefold case, but it's an important point, actually. So now let's going to talk about the elliptic Clavier forfold, the largest H11. So as you can see from the hash number, this is exactly a mirror of the previous one. So for the geometric gauge group on it, it's an enormous product group. So in fact, this geometric gauge group has already been worked out by this old paper by Philip Kandellas, Privarov, and Rajesh in 1997. So this is not a really new thing. And nonetheless, this is of course the largest gauge group that one can find in the whole known 4D N=1 landscape. Now, a very important thing, as I mentioned earlier, we can apply the Tate-Giada formula like this. So we subtract the rank of gauge group from the H1 of the Clavier forfold, and we can compute H11 of the base threefold to be about 180,000. And because for the F theory, the total number of axions is equal to the H1 of the base threefold plus 1, this model then naturally leads to the 40n equal 1 theory in the landscape with the largest number of axions as well. Okay. Now, a very important question is, what is the detailed structure of the base threefold and the vibration over it? And I'm going to extend in more detail in the next slide. So here, the construction of the base threefold is very non-trivial. It has four steps. First, I construct a non-compact toric threefold B8 with the following weird-shaped 3D polytope. So this is just a 3D polytope with 8 vertices. Okay. So after the triangulation of this polytope, the toric fan will have thousands of 3D cones, 2D cones, and more than 2,000 rays. So now, as you can see, the total number of divisors and rays in this toric threefold, so this 2,561, is exactly the same as the total number of EA gauge group in the physical theory. So this basically is a very important hint that we are going to tune an EA gauge group on each of these rays. Okay. So this is step 1. So now in step 2, so because the whole thing is still non-compact, and we finally want a compact thing, we want to add 2 particular rays into the BEA to make it compact. This step is pretty easy. So now after step 2, we still have an enormous base threefold with a lot of EA gauge group that's sitting next to each other. Then of course you expect that there exists a huge number of these non-minimal loci, either coordination 3 or coordination 2. And those things need to be blown out in order to get a good vibration in the end. So the blow up of these non-minimal loci are actually already studied before. So for the coordination 3, the collision 3 EA gauge group that was studied in this 4D conformal matter paper already. And for the blow up of the coordination 1 non-minimal loci, is a collision of 2 EAs that's completely the same as a tensor branch structure of a minimal EA-E8 conformal matter in 6 dimensions. Okay. So as a picture here, in the beginning, we have this toric diagram of 3 E8 sitting next to each other. So here, each point denotes a divisor, it's a ray, and the edge denotes a curve, and this triangle itself denotes a point. Then after a number blow up, you will reach this picture where we added a large number of new exceptional divisors, and each of them could carry some non-trivial gauge groups. Okay. So as you can see on each edge, so the sequence of gauge group is exactly the same as the minimal EA conformal matter in 6 dimensions. So there's also 2 remarks. So because here you can see that there's a triangle with G2, SU2, and type 2 singular fiber. So physically, that will correspond to the so-called coordination 3 non-minimal loci, which encode some higher order Euclid coupling. Also, because there exists a type 2 collision, so that will also lead to terminal singularity in the X4. Although in the definition of good vibration I just mentioned, those things are allowed, so it's okay anyway. Then finally, after step 3, I found out there are still a number of EA divisors with non-toric non-minimal loci that need to be blown up. And after everything has been blown up, we get this final base threefold B3 with exactly the correct Hauch number H11. And on the B3, the X4 is a good vibration. So we are done with this geometry. So now I'm going to make a few remarks, both mathematically and physically. The first one is, as I mentioned in this random blow-up approach, so this particular base threefold is also an endpoint base, but there's no way to further blow it up to get another sensible F3 base. Second comment is that this enormous geometric gauge group is already the non-hexagonal gauge group on the base threefold, and it's impossible to tune any bigger gauge group on it. Okay. The third point is that I also estimated total number of G4 flux choices, which is smaller than the one in the previous paper. And finally, this is a very important physical point. So besides the D7 brane sector, there also exists a number of D3 branes floating around here in the 4D physical picture. And the total number actually depends on the choice of G4 flux. So that will also lead to additional 4D gauge groups as well. The total number of these D3 branes is bounded by about 75,000. So this is basically physics and about this particular geometry. Okay. So now we can also ask this following counting question. You may wonder whether there also exists some other base threefold with exactly the same Hauch number H11 as this one, whether this is true or not. So in fact, even inside a single EA triangle, there already exists a huge number of flip and flop faces. So for example, instead of this triangulation, you can also choose to use the following one, which is quite different. And on this particular triangulation, it turns out that all the problematic things like conformation 3 for 6 loci and terminal singularity are completely removed from the picture. So in the end, the Clapeyron fourfold out of it can be completely smooth and flat. Okay. So I have proved that in a single EA triangle, there are at least more than 1 billion different flip and flop faces already. And then because in total we have 5,000 of these triangles, and all of them are mutually independent, and there's no further symmetry, then the total number of flip and flop faces for this space is this enormous number here. It's also amusing, there's an amusing fact that if we multiply this huge number by the total number of self-dual G4 flux choices, then this number will be bigger than that number on the Clapeyron fourfold with radius H31. So this is somehow just a bigger number. Okay. So now, besides the single geometry, as I'm going to also briefly comment on the phenomenological implication of this model. Well, the first one is pretty obvious. Because the total number of axions is pretty huge, it's at the order of 10 to the 5, it's very natural to consider the n-inflation scenario on this particular model. The second point is that there exists a huge amount of dark gauge sectors at the order of 10 to the 4th. However, the visible standard model sector is still very hard to construct from the D7 brane modes. And I would think that they are more likely from the D3 brane sectors instead. Okay. So it's for this geometry. And as I have mentioned before, there is this endpoint puzzle in the random blow-up program. So surprisingly, we can also explain that puzzle in a similar way. So the particular endpoint basis in the random blow-up program with this particular Hauch number can be constructed in a completely similar method. So we can just take another polytope, we triangulate it, and we tune an E8 on every divisor. Then we blow up all the non-minimal loci. And finally, we'll exactly get the correct B3 with the correct H11, which supports a very interesting Clapeyron fourfold as well. Okay. So this concludes my first part of my talk, the 4D Anchor 1. Finally, I'm going to briefly mention the situation in other dimensions, and many questions to this answer are actually known before already. For the case of 61,0 supergravity, we can ask what is the largest number of tensor multiplates and vector multiplates coupled to supergravity. In this case, the answer is And the particular model is F3 on the EDP Calabi-Yau threefold with the largest H11, and the total number of these fields are at the order of hundreds. It's also interesting that the structural base geometry looks like a non-minimal E8 conformal matter. Okay. So it's a 60 case. So for 5D n equal 1, the answer is pretty similar. So the largest number of vector multiplets that can couple to zero gravity is from the M3 on the same result Calabi-Yau threefold. But in this case, and there's a very interesting geometric limit. We can have a non-abelian quiver gauge theory like this, with some very huge SUN factors. And so there's a very interesting question that here I conjecture that SU96 in this particular quiver is the largest SUN gauge group that can couple to 5D n equal 1 zero gravity. And hopefully that may be answered by some swampland techniques. And so finally, I'm going to, for the lower dimensional case, like 2D 0,2, a natural point to study is F3 on EDP Calabi-Yau fivefold, and that's some ongoing work with Jiahua Tian. Okay. So finally, I'm going to conclude this talk with a few further questions. So given the boundary of the F3 landscape, there are two things we can ask. So we can either try to prove this bound is one-time constraint, or like, can we challenge the bounds in other parts of the string landscape, like M3 on G2 manifold? And of course, it's also pretty important, pretty interesting to further investigate the final implication of it. Okay. Thank you.
Okay, thank you. We can all use our reaction emojis to applaud. If anyone has a question, please say so in the chat window. Okay, so we have one question from Paul Konstantin Ullmann.
Oh yeah, hi Yinan, very nice talk.
Thank you.
I just have a quick question. So in the quiver you were showing in the last slide, yeah, that one. So there you have these curious jumps in the rank of the gauge group, right?
Yeah.
That they are jumping by 8 and they are always even. And this one looks a little bit like these quotient superconformal field theories that we have constructed like a couple of weeks ago with Fabian and Marcos. And yeah, for that reason, I just wanted to ask you, have you maybe checked if the ambient space of the generic fiber might have model-value torsion points that could lead to this global torsion quotient?
So sorry, this is a 5D case. So this actually, the quiver are like 5D gauge group that come from the compactification of a non-minimal EA conformal matter on a circle. So this was already studied by this paper, Omori, Schmidt, Yuji, and Unikura in the 2012 paper. This is not a new thing actually. Yeah, we also studied this in a recent paper in the like CFD and in our techniques. Yeah.
Right, I see. Okay. Oh, good. Okay, then. Okay, good. Thanks.
Okay, we have another question in the chat window from John Heckman asking, how does your classification story generalize if one allows O3 planes?
Let me see the chat. Oh, O3 branes. So you mean O3 branes in 4DF3? That's like analogy to D3 branes?
Yeah, orientable planes.
Oriental planes is O3 branes.
In particular situations where you may not have a Kreppin resolution of the Calabi-Yau fourfold.
Yeah, here I always...
That's in particular what I'm curious about.
Kreppin resolution until we only hit something only with terminal singularity. So if you add something that's a little bit more non-geometric, then of course I don't know the answer, but it will be very interesting to investigate the similar question and try to see whether we can exceed its bound or not. Okay.
Okay, we have a related question from Jim.
Hi, Yinan. Nice talk. So related to Jonathan's question, I was confused for a brief moment during your talk, and then I thought maybe it was resolved, and I wanted to ask. So you talk about the amount of D3 charge in this largest H11 example, which is, of course, chi/24. But it requires, of course, that you can actually compute chi, which normally we would do with the smooth variety, having some Crepin resolution. And then you talked about terminal singularities. And so I was wondering how you computed chi. It sounded like you flopped away the curves that were causing the terminal singularities and then computed in that phase. Is that right?
Actually, we don't need to do that. It's just like still a pretty usual budget construction of the hypersurface in the target space. And in that case, the Hodge number can even be defined even if there's still some residual terminal singularities. So the chi is still well defined by a subtraction of these Hodge numbers.
I see. So you have a definition of the Hodge numbers in the case of a singular variety with terminal singularities. I see. So that's the way to do it. Good.
Yeah.
All right. Thank you.
Okay, that's all the questions I see. Oh, we have one more. Jonathan Heckman again.
Yeah, sure.
Yeah, so you had a comment that you think the visible sector is more likely to come from D3 branes. Can you elaborate on that, other than just saying that there's lots of them?
Sorry, I haven't worked into more detail, but it's just like because there could be up to 75,000, and so I think in certain, if you have in the modularization, so after you do the modularization, then maybe certain D3 brane will collide with each other and they will be combined with some non-brilliant sectors. But I think nobody has ever investigated this question in more detail, so it's still a pretty hard question.
Well, the thought in some like quiver realizations, you might want something like a collapsing Del Pezzo 8, at least if you have a local Calabi-Yau threefold model. So the related question I would ask is, model it in terms of a local Calabi-Yau threefold. How many such geometries do you see where you have such an intricate like collapsing surface inside of the like local threefold? In order to get the struct, say, standard model or something, some extension thereof.
Oh, yeah, I know about this like kind of DPA with D3 branes.
Sure.
But I think.
So how common is it for that to happen?
So sorry, I haven't really investigated this question in more detail either. So
okay,
I can't provide an immediate answer.
Okay, thanks.
Okay, thank you. I think in the interest of time, we need to move on to the next talk.